everyone. My name is Primrose Pineda. On behalf of Park Systems, we'd like to thank you for joining us today for this webinar. Before we begin, I would like to give a short introduction on our speaker. Brian is the Application Senior Manager at Park Systems Singapore, where he supports customer demo requests and application modes training. He is also holding the Service Senior Manager position. With more than 10 years of AFM experience in service and application support for customers, Brian is well versed in various application modes like electrical, nanomechanical, magnetic, and fluid imaging modes in different research fields. So without further ado, it is now my pleasure to introduce our speaker for this webinar, Mr. Brian Lim of Park Systems Singapore. Mr. Lim, please.
Right. Thank you, Primrose, for the introduction. Good afternoon, everyone. My name is Brian Lim. I'm the Park Systems Application Manager based in Singapore. And thank you for attending this webinar. I see a lot of participants from all over Southeast Asia. We have quite a variety of participants. And today I shall talk more about the magnetic force microscopy, and then followed by a live demo. So I'm going to share what is MFM, give some application examples, and some hardware and cantilever recommendations, followed by the live demo. So what is MFM? MFM stands for magnetic force microscopy. It's actually a non-contact based AFM technique, and it's able to measure the surface morphology and also the magnetic properties of the surface, such as the magnetic domain, structure, and orientation at the nanoscale. So this is a schematic of a MFM working principle. So as you can see, there's actually this sample has some magnetic domains, and some of them are orientated up and or down. And when we have a magnetic coated tip, we're able to detect the magnetic force. So for the first pass, you'll be scanning the topography of the sample, and then it will move up at a certain height and scan in air following the height of the topography. And during this second pass, what it gathers is the MFM signal. So it's a two-pass method for the MFM. So magnetic force is between the coated tip and the sample are inversely proportional to the distance between them. So van der Waals force, such as repulsive and attractive force, act around the close distance between the tip and the sample, whereas the magnetic force is a longer range force. So basically, the leaf mode is able to separate the two forces. That's why you can get the topographic image and also the magnetic signal. So like what I said, leaf mode is a two-pass technique, right? So in leaf mode, the tip scans the sample surface twice. So the first pass is the topography. And then the second pass, it actually leaf up to a leaf height that we input in the software, and it actually follows the sample surface feature. And during this second pass, it actually gathers the magnetic signal. So based on how much the cantilever is deflected, it will detect the phase of the magnetic force. So as you know that if there's some magnetic domains, it will either attract the tip towards it or repel toward the tip upwards based on the polarity of the domain. So let's take a look at the effect of the tip and sample distance, the leaf mode distance. So if you key in 0 nanometers distance between the tip and sample, what you get is just pure topography phase. You don't get any magnetic signal. If you input higher value, like 20 nanometers, you may get the magnetic signal, and you may also get the topography signal interlaced into one image. But this is not what we want. What we want is the pure magnetic phase image. So we should leave to a height where we don't see any topographic effect on the phase channel. However, if you leave at a higher distance, you may also lose the signal strength. So let's take a look at some of the applications, right? So some of the common applications for magnetic materials are recording media, MRAM, ultra thin films, nanoparticles, spintronics, pattern elements, nanoclusters. This is example image of a hard disk, and a magnetic pattern array. So in this recording media, you can actually see this. If you zoom in into the phase image, you can see the recorded bit patterns, and then you can see with the signal to noise and ratio. So you capture both height and MFM phase in one image. Example 2 is a magnetic pattern array. So pattern array of magnetic nanostructures have become very important in the storage devices. So this shows the phase changes by time. So one more example is a magnetic vortex core. This is perma-alloy, and by MFM, we are able to find out, let's confirm the existence of this perpendicular magnetization. And if this is the zoom out image, the top one, and below is the zoom in image. And if you zoom in to one of the dots, you can actually capture the magnetization in the phase channel. So now let's take a look at some of the common components for MFM. These are the components that come with the MFM starter kit. Number one is a magnetizer to magnetize your tip. Number two is a clip where you put in your tip and you can orientate the polarity of the magnetization of the tip. And the third is the non-magnetic clip type sample holder. So this is to eliminate some other magnetic force of the magnet sample holder. So we change to this non-magnetic clip type sample holder. So now let's talk about cantilever. So for MFM, generally there are 4 types based on the magnetic properties of the sample and the purpose of the sample measurement. So there's MFMR, standard probe, LM MFMR, samples with for samples with strong magnetic fields. LM stands for low momentum. At LC MFMR, low coercivity, for samples with weak magnetic fields, and SSS MFMR, which stands for super sharp tip, for high resolution imaging. Right. So these are some of the common specifications of this cantilever, and they are all coated with this magnetic coating on it. So let's take a more detailed look at the cantilever. So we can divide into three criteria: tip radius, coercivity, and magnetic resonance. So coercivity is how the probe changes the magnetic polarity, right? So if for LC, that means the probe can change the polarity very easily. So if you have a very strong magnetic sample, you will not choose LC MFMR, and you should choose MFMR or LM MFFR. So for resonance magnetization, it is telling you how sensitive the probe is magnetic field. So the higher resonance is the more sensitive. So MFMR is one of the highest at 300. And also LC MFMR is also pretty high. LM is slightly lower, and SSS MFR is slightly lower. So cantilever preparation. This magnet is actually used to change the polarity of the cantilever. If you do not need to know the polarity, it is not necessary to use this magnetizer, right? So if you see the magnet of this polarizer, it has a north pole and a south pole. And when you load your tip, depending on which, you can load your tip into this bracket, cover it, and you can insert it into this magnet. And you can insert it in both directions, either tip up direction or tip down. And depending on which direction, you can magnetize the tip according to the direction you want. So some additional hardware is a MFG, magnetic field, external magnetic field generator. So if you can see, this is the NX10, and there's a magnetic field generator, which is connected to a DC power supply attached to the head. So when you approach on the sample, you can apply magnetic field based on how much voltage you apply to the MFG. So this is a variable external magnetic field generator, and it applies in the direction of the in-plane. We also have an option for out-of-plane magnetic field generator, which is being developed right now. So if you have any interest, you could approach us on that. So this is an example of MFM image using the external magnetic field, right? So this is with zero Gauss magnetic field, and we cannot see any magnetic domains when we scan. However, when we apply DC voltage and up to 300 Gauss, we can see the magnetic domains very clearly in the MFM phase channel. So some additional info. So MFM, if you do MFM in the high vacuum it will also increase the MFM sensitivity by several fold. So the reason is because in vacuum, the resonance curve, the Q factor is much higher. So when you have a much higher Q, a sharper peak, a more focused peak of the resonance frequency, you can get a very good increased MFM sensitivity. So they have done studies and they found this, and Park systems also offer this NX high vac, which is the AFM in a high vacuum environment. So this NX high vac is very good for electrical measurements where you require no moisture, like conductive AFM, scanning spread resistance, and also MFM. Okay, so now I shall go on to a live demo. Okay, so let me share the screen of my software. All right, so this is our smart scan software, and I shall show the video. This is the NX20. So the NX20 is a large sample stage, and so this is the head, so on and so forth. But I shall stop the video now, and I want you all to look at the software instead, because this is where all the action has taken place. So I have already aligned the cantilever, aligned the laser, and I'm going to change the mode to MFM. So first, I will change the cantilever name to MFMR. This is the tip which I've loaded. I should change the mode to MFM. So it does a automatic frequency sweep to find the resonance frequency. So I would prefer to make it slightly lower, slightly lower amplitude. Okay, so the sweep is quite good at 80 Hertz, which is close to our resonance. And I shall add the channels. I'll add the MFM channels. Okay. And now I shall start to approach the sample. Create a folder. Okay. So this sample is a hard disk sample. It's one of the standard sample in a MFM kit, and I'm going to approach on it now. Start scan size at 0. Okay, so this sample is a bit dirty, so sorry about that, but I believe we still can get some MFM signal. Okay, so now the sample is approached and we can scan at the slower speed and a bigger area. So first I will make sure that the topography, the height channel is well optimized. If not, then I can do some simple adjustment of the parameters. Make sure that the trace and retreat forward and backwards are well matched. Okay, so this is the MFM phase, which you can see that actually there's not much variation. So what we're going to do is going to apply the leaf mode, enable the leaf mode, and we can control the distance. So right now at 50 nanometers, I get to see some contrast. And we can start to scan to see if we can get a clear signal. So let's turn on the height. So this is the height channel. Sorry. Okay, so there's this function which calls skip scan, which I will turn on later, but I'll start with the normal one. Okay, let's start. So we can take a look at the two channels by looking at two channels at one time. And so you can see that there's some regions which has magnetic domains here. So this is the phase channel. So you can see some magnetic domains right here, and some areas which do not have any magnetic domains. So we can also change the angle of the rotation of the scan. If you want to see, sometimes by changing the angle, you can see things clearer. So this is the height, and this is the phase. So as you can see, there's no interlap of the topography channel on the phase channel. So let's try to complete this scan before I change some orientation. Okay, so here you can see there's no magnetic signal right at the end. So I like to go through some of the parameters in this leaf mode while we are scanning. Okay, so it's gonna take like 6 minutes. So maybe we should try to reduce some of the scan rate. I can increase the scan rate slightly. Okay, so first is the tip and sample distance, and then followed by the second pass options where you can apply some kinds of options like turning on the tip bias. So you can apply tip bias when a tip is actually scanning in air, detecting the magnetic domains. You can apply up to plus minus 10 volts. And you can also turn on the non-contact mode drive frequency, a drive to the topography. You can also turn off the AFM laser, but however, if you turn off the AFM laser, probably you will not get any MFM signal. So the last one is to follow the slope line. Okay, so this follow slope line means that if the AFM is going up a slope, you will just follow the slope, but you will not follow the features. So let me try to see if I can share an example of this slope, what it means. Yeah, I'm going to share to another document and y'all can take a look. So this is what it means by slope. If you turn off sample, follow the slope line, you will just follow the slope, the black one. So you may hit some of the features, but if you do not click on the follow slope, then you will just follow the features as well. And number 5 is you can have a square wave coming out of the controller, back of the controller in a BNC connector. You can check the leaf state. So the first pass 0 volts and second pass you get 5 volts, and this is very good if you want to have some kind of customized experience for your MFM. Okay, so now let's go back to my software. I should be finishing the scan in 1 minute time. So this is MFM. So after the image is done, we can do some basic analysis. The XEI program is very easy to use offline analysis, and I'll show you how to do that in a very short while. Okay, the scan is ending soon. All right, so I'm going to open up some channels. Okay, and I'm going to share the channel. This is the XEI which I'm going to share. So this is the topography channel, which needs to be flattened. Right. Topography. And this is the phase channel, which I'm not going to flatten. Right, so I can compare 2 channels. I can draw some lines. So you can compare some of the contrast of the phase. So some areas are without signal, some are with magnetic signal. You can also put in some cursors where you can average out, like to find out how strong is the region. You can share like average cursors to find the strength of the magnetic field in degrees. So for this one is in the green region and it's Y2. Right, so you can also do analysis, multiple lines, and compare. Right? 2 lines, compare side by side. So all these are magnetic signal without any topography effect. Okay, so you can also like do a 3D. So this is a 3D profile of the height, and we can just overlay this magnetic signal to this height profile. Okay, so some basic analysis, and I go back to my software, and so as you know that this is pretty slow, and we can also improve. We can change the rotation. Can change the rotation of this scanning. Scan some region, cleaner region, right? So we can do the skip scan. So in this skip scan, we only get the forward signal. So if we do a skip scan, then we get just the forward signal without the backward signal. So you get only one set of data, but sometimes you get more faster data. Okay, so you are seeing sometimes the resolution can be a bit higher. We use skip scan, and if you scan slower as well, you can get a better MFM signal. Okay, so as for the tip sample distance, this is an example like if I increase the tip sample distance to high, then the MFM signal becomes very weak. Like from here onwards at 150, you don't get much signal. However, if you reduce too much, it may be a bit dangerous. So I'm going to keep to maximum 30, 40. So the lower leaf height, the stronger the MFM signal. Okay, so this is the end of my live demo, and I will take some of the questions that I've seen. So one of the question is, how does the system ensure that there's no tip interaction? There's no tip interaction with the applied field when the MFG is used. Okay, to answer your question, I think I have to share some documents. So, let me share some documents. This is more on the hardware side. Okay, I'm gonna share one page of this external MFG. So these are the components of this MFG, and this is the magnetic field generator, DC power supply with a clip type probe hand, the jig. So during the setup, the MFG is actually applied right here, and we only apply it after the sample is, the tip is approached on the sample. So in a way, it is slightly below the tip. So you're applying the magnetic field on the sample. So this is the plane of the magnetic field. So you're applying in the in plane of the sample, not on the out of plane of the tip. So this is the external magnetic field, and the external magnetic field is applied in plane, so you will not affect the tip that much. So then look at some other questions. Okay. What maximum size your sample? So for my sample, for this, I'm going to show my video. It depends on this sample stage can accommodate up to 150 mm, or we can have sorry, do you mean is a scan size? If the scan size, we can scan up to 100 microns. 100 microns is the maximum scan size that we can scan on the AFM. Okay. All right, so I believe that's about it.
All right. Yeah, thank you, Mr. Lim, for that very informative talk.
You're welcome, Prim.
Okay, so it seems that that is all the questions that we have so far. So you can continue to type in questions as we wrap up. And if anything comes in, we will reach out to the attendees via email afterwards and answer all those questions. So on behalf of Mr. Lim and the rest of the staff here at Park Systems, thank you all for making time amid your busy schedules to join us here today. It's been our pleasure to host this webinar, and we hope to see you again at our future webinars from Park Systems soon. Take care, everyone.
Thank you very much. Goodbye.